Okay, this is 1.2a, the first of a couple videos in college algebra. And we're on page number 28, top of the page, section preview, where it talks about aging workers. And it says the millions of Americans who are working full-time at selected ages from, and this is important, 20 to 65, can be modeled as a function of their age x. All right, so here's the formula, the model. Okay, again, you don't have to understand where this model or where this equation came from. I'm trying to talk and write all of these numbers at the same time. See if I have enough room here. Yeah, I'm not going to have enough room. Minus 1.339x. All right, let's slide this over a little bit. Plus 21.7. Where in the world they came up with that equation, oh gosh, no idea. But there it is. And that's all we care about, is that we've got the equation. You don't have to understand where it comes from or how they developed it. So to graph this function, we use x values from, what I said was very important, 20 to 65, because that is the age here. So x can be any number as long as it's from 20 to 65. And we put those numbers in there for x. So if we decide we want to find out how many Americans are 20 years old and working full-time, we put 20 in there, 20 in there, 20 in there, and solve it. If we want to find out how many Americans are working that are 65, we put 65 in there. So to graph that, we use x values from 20 to 65 and then find our y values. And we've got our graph. And when we do that, we end up getting, some graph. I have no idea what the graph looks like, but let's say it looks like this here. So this is at 20. And this is at 65, so it's got to be between there, and let's say that it kind of goes like this. Okay, so as you get closer to 65, there's fewer working than at 20, most likely, but who knows. Anyway, that's just a guess of what that graph is like, because you're going to put in 20, 21, 22, and it's going to spit out a y value, okay, and then you're going to plot those points on the graph, and you're going to get a graph that looks like, well, whatever it looks like. I'm just kind of throwing one out there. All right, so one of the things to remember, or to notice, this is a function. We put 20 in here, and it's going to spit out one number. We put 21 in here, it's going to spit out one number. It's not going to give us like 104 and 30 when I put 21 in there. It's only going to give me one number. Very, very important to understand and to realize. So one of the important things that we're doing here when we're graphing functions, or graphing these equations that we're going to be working with, is we can sketch the graph of that function by coming up with enough values for x to give us a y value, so that we can start putting those points on our xy axis, so that eventually we'll be able to draw a nice smooth curve that gives us a reasonable idea of what the graph is going to look like. Now, this is called a point plotting method of sketching a graph, okay? Because what we're doing is we're finding points, we're plotting those points, and then we're able to come up with a graph. Now, the biggest concern that you run into is, do I have enough points in order to give an accurate graph of what I'm needing? Okay, and that's one of the things that we're going to be doing in the class, is by looking at the equation, you can find a few different secrets that are going on with the equation that will help you get an idea of whether your graph is a reasonable idea of what you're looking for. All right, so let's look at example 1 here. So in example 1a says graph the equation, and they give us the equation here, and they say that the equation is y equals x squared. So Graph the equation by drawing a smooth curve through points determined by integer values of x between 0 and 3. So they give us the numbers that they want us to plot. Numbers between 0 and 3. Integers. So that means just the counting number. 0, 1, 2, and 3. And you put those numbers in for x here and see what you get. 0 times 0, 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. So there are 4 plots you can put on your graph. And if you look at A here, that's exactly what we have. We have our points 0 and 1 and 2 and 3. Now the problem is we haven't used, not only have we not used enough numbers to give an accurate graph, and one of the things that will help you is if this exponent is a number greater than 1, you're going to need quite a few more points in order to plot. In fact, and this is one of those, not secrets, but one of those tips. The bigger this number is, the more points you're going to need in order to get an accurate graph, because the more complicated the graph is going to be. If there's only a 1 on here, you know, there's just like x plus 2. If you have 3 points here, that's plenty to draw the graph. But if you have a 2 on here, you're going to need more than just 3 points. You're going to need more than 4 points. You're going to need a variety of points, both positive and negative numbers for x, to see what happens to this graph when we do that. Right now this graph only does this. But notice what happens. When I start putting negative numbers in here, my graph not only gives me this, but it also moves this way as well. So this is an incomplete graph because I haven't used enough numbers and a variety of numbers, both positive and negative, in order to find out what an accurate rendition of this graph is going to be. This is called a complete graph. When you have pretty much looked at the unseen parts, like over here, and fill them in and have a graph that is accurate and complete. So again, the bigger this number is, the more points you're going to need. And the problem is, let's say this is a 4, x to the 4th. That means you're going to need more than just 8 or 10. You're going to need probably 15 or 20 points, really, in order to get an accurate idea of what that graph looks like. And that's why graphing calculators come in handy, and that's why coming up with different tips will help you to determine whether you have enough points, because you're graphing this and you're starting to plot it and you're like, okay, according to the equation, this should be more complicated than this, so I must be missing some things. So it kind of gives you an idea of whether or not you're kind of going in the right direction. All right, so complete graph, middle of page 29. A graph is complete if it shows the basic shape of the graph and important points on the graph. Important points on the graph is very obviously important. And we'll get into what those important points look like. But let me just kind of give you an idea of what an important point looks like. So we have a graph here. And let's say this graph does this. Okay. What are the important points? The important points are where it crosses the x-axis. Other important points are the highest and the lowest points on the graph. These are called turning points. That means we're turning from going up to going down to going up to going down. Okay? So those are some important points. Also an important point is where it crosses the y-axis. Although that doesn't seem to be as important as where it crosses the x-axis, and knowing where the turning points are, or sometimes they call them the vertexes or vertices of the graph. I prefer turning points myself, okay? So those are some important things. And what else does it say? And suggests what the unseen portions of the graph will be. See, there are some parts of this graph that we can't see. We can't see what's going on over here. But we do know that this graph is kind of going down consistently, and pretty soon it's going to keep going and keep going further and further in this direction, and as it goes further and further down. So we can kind of get an idea of what's going on there. And we'll talk about that in future lessons, about what you call that area down here that you don't end up graphing. All right, let's look at example number 2. sketch the complete graph of the equation. Let's get some junk out of here. And the equation is f of x, which again just represents y, x cubed minus 3x. Okay, remember what I said about this number here is the bigger it gets, the more complicated your graph is going to be and the more points you're going to need in order to solve that. One of the little clues here is you can determine how many turning points there are based on that number. Whatever that number is, if you take one away from it, that gives you the number of turning points. Sorry about my cursive on this, but you know what I'm saying because I said turning points, so even if you can't read that, that's what I mean. Okay, so there is our equation. And notice they've got the table 1.11. They plugged in 3 negative numbers, they plugged in a 0, and they plugged in 1, 2, and a 3. And they end up getting a graph that looks like the one at the top of page 30 that goes through point 0 and kind of looks like that. And notice they put arrows on it showing that it goes into infinity in both the x and the y direction. As you move this way, this gets bigger and bigger. As it goes this way, my y value gets smaller and smaller into the negative direction. So, one of the problems you run into is when you don't have technology, when you have an equation like this, you end up with a real struggle. Now, there is a free graphing calculator that you can use on your iPad. I have it on my phone, and it's called Desmos. Okay, and what you can do then is you can type this equation in there, hit a button, and it will show you that graph. In fact, you can use your 2 fingers, and you know how you make images bigger or smaller? You can do that with the graph, and you can just look at different parts. You can just look at, say, this part of the graph, or you can spread it out and look at the whole graph from like, gosh, negative 1,000 this way to positive 1,000 that way, and see if anything else happens somewhere in there. Probably not. Okay, usually what happens is going to be right in here, and the rest of it is going to be consistent. You go this way, and it's not going to all of a sudden out in the middle of nowhere make a quick turn like that. It's going to pretty much keep going in that direction. So when you're on page 30 and 31, it talks about using a graphing calculator. Now, this will show my age. When I was in high school, they just came out with calculators that added, subtracted, multiplied, and divided. That's all they did, and they were $200, and they were huge. They were about the size of an iPad. And as I got older and started going to college, they started coming out with the scientific calculator, and I learned to teach math, and I learned my math using only a scientific calculator, which meant I had to understand how to graph and how to do this stuff by hand instead of having a graphing calculator at my disposal, which was a good thing because now I understand why the graphing calculator works. I understand how to put the information in there and how to read the graph, and so that's the direction that I teach. I allow you to use graphing calculators. In fact, I expect you to, even if the graphing calculator you use is Desmos, and just go to the App Store in either Apple, or mine's on my Desmos. It's an M, sorry about that. I go to use on my Android, and it works really, really nice. And I'm not going to go over how to use the graphing calculator because every graphing calculator is different, okay? And because I don't use all of them in order to teach you all the difference there. All right, so let's go to example number 3. Okay, so if you decided that Desmos might be a direction you want to go, here's the screen that opens up when you do it. And it's on my phone. And it's just going to kind of go look at an example, graphing a complete graph For example 3, it gives you an idea of how to use a graphing calculator and tells you how to do it and set up your minimum and maximum and all that kind of stuff. I'm just going to show you on Desmos because that's the one I have at my disposal. So right here, you type in y equals x, and then you click on this button here, and then you click on 3, and that will give you x cubed. So it means x, and this says, okay, what do you want the exponent to be? 3 minus 3x, and then you click on this squared because of the squared, so because that just means it's going to put a square. You could click on this and put a 2 there, but it already gives you that option. Minus 13, and then you hit equal, and it will show you the graph here. Now again, you can take your 2 fingers and go out or in or whatever, and you're going to get a graph. Bottom of page 31. A, if you bring it in real close, and B, if you take it out. And it gives you an idea of where that graph does some crazy stuff. Now, it only does it close to the origin there of the graph. It doesn't do it way out in the middle of nowhere somewhere. So anyway, that's just an easy way to use this graph. If you even go to example 4, on page 32, you have the same opportunity. In fact, what they do on example 4 on pages 32 and 33 is they go into using an Excel spreadsheet. You can do all these formulas on Excel. Now, if you're a business major, you probably know how to use Excel and know how to use the formulas and don't have any problem with it. If you're not, you probably just want to stick to the calculator because there's quite a learning curve, I think, in order to put these formulas in there. So what I want to do with example 4 is just talk through, what the heck is going on here. Okay, so we've got C equals 5350 P over 100 minus P, and that is in dollars. All right, so let's see what's going on. Use the restriction on P. Okay, what in the world does that mean? Well, look at what they're saying. Suppose that the cost C of removing P% of pollution. So we're removing a percentage of pollution. So we are restricted then that our P can only be a number between 0 and 100 because percentages are 0 to 100%. You're not going to remove more than 100% of the pollution, and you're not going to move a negative percent of pollution. So it's a number between 0 and 100. So that's your restriction on P. Okay, so it has to be a number somewhere between there. So P is restricted to, has to be either 0 or greater than 0, and it has to be less than 100%. It's not going to be 100% because what happens is if I take this 100 here and put it here, I end up with a 0 down there, and when I have a 0 in the denominator that's undefined, it's not a possibility. So that's what I looked for here. It's like, oh, so that has to be just less than 100. It can be 99.999, but it can't be 100 because it makes that denominator undefined. So just something to consider as you are determining your restrictions and what your answers can be. All right. B, graph the function on the viewing window, and why is it reasonable to graph this model on a viewing window with a limitation of C is greater than 0? Okay, C is greater than 0 because the interval contains all possible values of P. It has to be 0 to 100. Okay. Now, C can be any number, but C has to be positive because remember, C has to do with money, okay, because of the dollars right here. So C dollars. Well, we can't have a negative amount of money. So if we're talking about the cost of removing pollution, you can't have a cost of removing pollution be less than 0. It has to be a number, a positive number. So therefore, it's bounded by 0, which means if we were to graph this, it could not go below 0 here. because then it would be a negative dollar amount. Okay, and then the final part of this, C, in example 4, find the point in the graph that corresponds to P equals 90. So really all I have to do is take 90, put it in here, multiply, divide, and I will find C. Okay, or I will find the number that corresponds with 90. So if this is, say, 90 here, then I just go up here and I can find out what the value is. And in this one, it's $48,150. All right, so you can do that with the spreadsheet, play around with Excel if you want, or be happy just using a calculator, Desmos, or whatever direction you want to go. So that's it for 1.2a. We will continue with 1.2b.